In this lecture, we shall discuss the basic principles of radiative transfer, basic principles of absorption and emission of radiation. Let us go back to a puzzle that we had posed in the previous lecture. If you recall, when one looks at the spectrum of the light from the disk of the sun, one sees absorption lines. Whereas, when one looks at the limb of the sun, for example, the chromosphere just before a total solar eclipse, one sees emission lines. Why is this so? This is what we are going to try to understand using the basic equation of radiative transfer. First, let us introduce the notion of specific intensity or brightness. This is a rather important concept, and you must pay attention to the units and dimensions of the various quantities that I shall introduce. Let us consider an elemental area dA, and there is radiation incident on it from the left and going through to the right hand side. Let us concentrate on the radiation that flows into a narrow cone of solid angle d omega, with the axis of the cone indicated by this unit vector n perpendicular to the surface area dA. Let us discuss the energy crossing this area dA in a time interval dt in the frequency range nu to nu plus d nu and going into this solid angle d omega. That energy defines our specific intensity or brightness through this relation that dE is equal to I nu, the specific intensity at the frequency nu multiplied by dA into dt into d nu into d omega. The most important property of the specific intensity or brightness is that it is a constant along the ray. It does not decrease with distance, unlike the concept of intensity which we normally somewhat loosely introduce. Now let us consider a volume, a small cylinder of cross-sectional area unity and filled with radiation, filled with photons. And we are interested in the photons which will come out of this surface and go in the direction indicated by this cone. Now, it is clear to you that in a time dt, photons inside this cylinder, whose length is c dt, where dt is the time interval that we are considering, and c is the speed of light, I'm sure it is obvious to you that all the photons inside this elemental cylinder will, in a time interval dt, pass through this surface and go into this cone. Therefore, one can define a relation between the specific intensity I nu, which, if you remember, is the energy going into this cone, and the energy density U nu of the radiation or the photons going in this particular direction. And the relation is the specific intensity is equal to the speed of light multiplied by the energy density of the photons going in that particular direction and into that solid angle d omega. And U nu is the energy density per unit solid angle per frequency interval, So, all I'm saying is that as long as I'm considering a cylinder of length c times dt, then I am guaranteed that all photons moving in this direction will go through this surface and enter this cone in a time interval dt. Now let us define the emission coefficient of a medium. emission coefficient is usually denoted by J nu. The spontaneous emission coefficient J nu is the energy emitted per unit time, per unit solid angle, per unit volume of the substance. In other words, if dE is the energy emitted in a volume dV in a time interval dt into a solid angle d omega in the frequency range d nu, then this relation defines the emission coefficient J nu. The dimension of the emission coefficient is energy per volume, per second, per hertz, per steradian. Now let us consider a medium, for example a cylinder of a cross-sectional area dA, and then we ask what is the contribution of this medium to a beam of radiation of cross-section dA. In other words, what is the intensity added to the beam by spontaneous emission in a length ds of the cylinder, and of course if we integrate it, we will get the radiation from the entire cylinder. That relation is the specific intensity added to the beam of cross-sectional area dA is given by the emission coefficient G nu into ds. If the length of the cylinder is increased from ds to 2ds, then the contribution to the specific intensity will double, and so on. Now let us introduce the absorption coefficient alpha nu. The absorption coefficient is defined through the loss of brightness in a beam as it travels a distance small ds. In other words, specific intensity is incident on the cylinder. It is the loss of that brightness per distance ds as it traverses the cylinder, and it is denoted by alpha nu. And that is obviously given by this relation, that the change in the specific intensity due to absorption is given by alpha nu I nu. That fraction is eaten up by the material over a length ds. And the fact that it is a loss of brightness is indicated by this minus sign. Traditionally, because I have put a minus sign there, the absorption coefficient alpha nu is taken to be positive by convention. That's why we have put a minus sign there. So that defines the absorption coefficient. So we have now defined what is added by the medium in a length dl, that is J nu into ds, and what is absorbed by the medium in a length dl, which is minus alpha nu I nu. The dimension of alpha nu is inverse length, centimeter to the minus 1. Now let there be n absorbers per unit volume of this material, and let each absorber have a cross-section sigma nu. The dimension of sigma nu is an area, centimeter squared. If you remember, in the previous lecture, we discussed Thomson scattering of radiation by free electrons. And in that context, we introduced the Thomson scattering cross-section as 8 pi by 3 square of the classical electron radius. Similarly, for various absorption scattering processes, there are different cross-sections, and quantum mechanics tells you how to calculate this cross-section. For us, what is important right now is to appreciate that this absorption coefficient is clearly related to absorbers, each absorber subtending a cross-section sigma nu, multiplied by n, where n is the number of absorbers per unit volume. So you see that the dimension is right because n is 1 divided by centimeter cube. Cross-section sigma is centimeter squared. Therefore, n sigma is the dimension of centimeter to the minus 1. So that agrees with what is expected over there. us write down the basic equation of radiative transfer. I have brought down ds from the right hand side to the left hand side and written it as a differential equation. di nu by ds, the change in the specific intensity over a length ds, is the sum of two terms. It is the emission by the medium J nu with a plus sign, and an absorption by the medium, a fraction alpha nu I nu is absorbed, and absorption is indicated by a negative sign. Now let me introduce the important concept of an optical depth tau nu. The optical depth is the integral of the absorption coefficient over the length of the medium through which our radiation is passing through. So the radiation is passing through a cylinder of length capital L. For a length ds, the fraction that is absorbed is alpha nu I nu ds. Therefore, the total amount absorbed over a length L is the integral of alpha nu ds integrated from one end of the cylinder to the other end of the cylinder. So, optical depth depends upon the depth of the material over which the absorption is taking place. Clearly, that is a number. The dimension of alpha is centimeter to the minus 1, ds is centimeter, therefore optical depth tau nu is dimensionless. One says a medium is optically thick if the optical depth is greater than 1 or much greater than 1. And one says a medium is optically thin if the optical depth is less than 1. For example, a brick wall is optically thick, it is opaque. The optical depth is infinity. No radiation from behind the brick wall can get through it. Whereas the air is optically thin and its optical depth is less than 1 because air is transparent to visible light. Now let us go back to the equation of radiative transfer which I introduced. di nu by ds is minus alpha nu I nu plus j nu. This is the absorption by the medium, this is the emission by the medium. Very often, this differential equation is written differently by dividing both the left-hand side and the right-hand side by alpha nu. Because if I divide by alpha nu, I will have alpha nu ds, which is d tau nu. Therefore, this differential equation can be cast in this form. Instead of di nu by ds, I now have di nu by d tau nu, where tau nu is the optical depth at the frequency nu, and the first term is I minus I nu because I have divided by I nu, and the second term is the ratio of the emission coefficient J nu divided by the absorption coefficient alpha nu, and that is traditionally called as the source function. Having introduced this notation of the source function, I'm going to change the symbol for it, and I'm going to call it I nu b. That is the specific intensity corresponding to the body through which the radiation is going. Therefore, the equation of radiative transfer, this is where we started with, by dividing by alpha and writing it in terms of optical depth. What we have is di nu by d tau nu is equal to minus of I nu minus I nu b, where I nu b is the ratio of the emission coefficient to the absorption coefficient of the medium. So this is the contribution of the medium to the specific intensity. So this is the same equation as in the previous slide, carried over here so that you can see it readily. And to remind you once again, I nu b stands for I nu body or I nu medium, which is the ratio of emission coefficient to absorption coefficient. Now this equation can be integrated very easily. It is a very simple first order differential equation. It is of the form dy by dx is equal to minus y. That can be cast by bringing this to this side and this to that side. It can be written as dy over y is equal to minus x. integrating both sides, I get log y is equal to minus x. Therefore, y is equal to e to the power minus x. So that's all that I have done over here. If you have studied some differential equation, please verify this. It will take you about 30 seconds. If you have not studied differential equations, please accept this equation as I have written down. Now I can take this term, second term on the left hand side to the right hand side and rewrite the equation in the following form. I knew the specific intensity coming out of this medium is the specific intensity incident on the medium multiplied by e to the minus tau nu plus the specific intensity added by the medium but multiplied by bracket 1 minus e to the power minus tau nu. Now this is the basic equation of radiative transfer. Now if you are woken up in the middle of the night many years from now, you ought to be able to write down this equation. Not from memory, but using the principle on which this equation has been written. So let's try to understand that. This is the same equation as in the previous slide. There are two terms. This is the first term and this is the second term. This is the specific intensity incident on this medium and this is the specific intensity going out. Now let us try to look at the meaning of these two terms. This is the first term on the right hand side. Clearly what that's trying to tell you is that the incident intensity is attenuated by a factor e to the power minus tau nu. What about the second term? Let us take this medium and chop it up into a series of little slabs. The first slab emits a certain amount of radiation, I nu b, and that radiation is partly absorbed by the second slab, but the second slab also contributes to the radiation. Now that impinges on the third slab which absorbs part of it, but it also contributes to the radiation, and then the fourth slab and the fifth slab and so on. Therefore, the second term on the right hand side is the contribution of the medium to the specific intensity, but the medium itself self-absorbs part of it, and that is denoted by 1 minus e to the power tau nu. Why is there e to the power minus tau nu? Please remember, in every case I am absorbing the same fraction alpha. So I have a geometric series, alpha, alpha squared, alpha cube, alpha to the power 4 and so on. When I sum it, I get an exponential function. Now, so that's the equation of radiative transfer. Now let us look at it in the two limiting cases of optically thick medium and optically thin medium. By that I mean if this medium is optically thick or if it's optically thick. When the medium is opaque, that means the optical depth of this medium is very large compared to 1 tending to infinity. Then when I look from this side, I won't see any of the incident radiation. This is like a brick wall. The medium is opaque. Therefore, what I will get is only the radiation from this opaque medium, which is at a temperature T. So what do I expect? I expect the spectrum of that radiation to be the Blackbody spectrum, because Kirchhoff taught us in 1860 that a black body or an opaque body in thermodynamic equilibrium emits at all frequencies, and the spectrum is given by a universal function which is a function of the temperature, and this function itself was derived by Max Planck in the year 1900. And that spectrum is given by 2h nu cubed by c squared multiplied by 1 divided by e to the power h nu over kt minus 1. Now you will say, I have studied Planck's law, but it doesn't look anything like that at all. I know there should be an 8 pi in the numerator and there should be a c cubed in the denominator. You are absolutely right. That is because you are not used to seeing Planck's law written in terms of the specific intensity I knew. You are not used to seeing Planck's law written in terms of the energy density of the cavity you knew. And that relation is the energy density is the specific intensity divided by the velocity of light. Now that is the energy density of photons going into one particular solid angle d omega. But we are interested in photons going in all directions. Therefore, I integrate over the solid angle and I will pick up a factor of 4 pi. So when we are finished, we will pick up a factor of 4 pi divided by c, because this c will go on the left hand side. And therefore, this expression, which you are not familiar with, the black body spectrum written in terms of the specific intensity, is the same as Planck's law. And Planck's law does indeed read 8 pi h by c cube nu cube e to the power h nu over kt minus 1 d nu multiplied by the volume of the cavity. So that is Planck's law, written here once again for a particular purpose. Now it is customary to look at this black body spectrum in the limit of low frequencies and high frequencies. Now in physics, low and high, small or large have no meaning. It has to be compared with something. What do I compare frequency with? Well, it is more easy to compare h nu, which is energy, with some other energy. What other energy can I compare it with? Kt, which is the thermal energy of classical physics. So we can ask, what is the limiting form of this expression in the limit where h nu is much smaller than kt, which is classical limit, but here I'm going to write down the limiting expression for h nu much greater than kt, which is the quantum limit. And the quantum limit of Planck's distribution is u nu d nu is 8 pi h v by c cube, nu cube, into e to the power minus h nu by kt into d nu. Why? Because when h nu over kt is very large compared to 1, this first term in the denominator is large compared to 1 and the 1 can be dropped, and this exponential can be taken to the numerator and it becomes e to the power minus h nu over kt. Now this expression is known as Wien's formula or Wien's displacement law. Why is it called displacement law? That is because we would like to know where is the maximum of this Planck distribution. If you remember, the Planck distribution is a bell-shaped curve. At what frequency or what wavelength the maximum occurs? Let us consider it as a function of frequency. Clearly the maximum will occur when the denominator is minimum. That is going to be around the value when h nu is approximately equal to kt. That is when the denominator is going to be minimum, and therefore the fraction, the ratio is going to be maximum. So here is Planck's distribution, the intensity versus wavelength. I could have just as well plotted intensity versus frequency. And I am asking, what is the wavelength at which the maximum occurs? And I already said the maximum will occur at a frequency which is h nu is approximately kt. Now this can be written in terms of wavelength by writing the frequency is in terms of wavelength, and that would read as follows. The wavelength at which the maximum occurs of the black body spectrum, written in centimeters, is 0.3 divided by the temperature in Kelvin. What it means is if the temperature of the body is very low, the wavelength at which the maximum will occur will be a very long wavelength, or the frequency will be very low frequency. On the other hand, if the temperature of the body is extremely large, then the wavelength at which the maximum occurs will be at small wavelength, and the frequency at which the maximum will occur will be at very large wavelength. So here is an example. What I have plotted is the brightness of the specific intensity as a function of frequency increasing from left to right of various black bodies ranging in temperature from 0.1 Kelvin, 1 Kelvin, 10 Kelvin, 100 Kelvin, all the way up to 10 billion Kelvin. When the temperature of the body is a few Kelvin, the maximum occurs in the microwave region. Whereas if the temperature of the body is 10 billion degrees, the maximum will occur at frequency corresponding to ultra high energy gamma rays. Do we have a situation where we have a black body at very low temperature of the order of few Kelvin? Yes, indeed. The universe is filled with black body radiation whose temperature is 2.74 Kelvin. This is known as the cosmic microwave background radiation. And what is the origin of this radiation? This is the relic of the primeval fireball. When the universe was very young, it was very dense and very hot. And the radiation, which peaked at a frequency corresponding to ultra high energy gamma rays, has now cooled and peaks in the sub-millimeter wave region. We'll come and discuss this radiation when we talk about cosmology towards the end of this series of lectures. Now let's go back and state some very important principles that one can infer from this principle of equation of radiative transfer. The first term on the right hand side, which is this term over here, is the intensity of the incident radiation attenuated by the body, e to the power minus tau nu. And the second term is the intensity added by the medium but self-absorbed by the medium itself. So there is a factor 1 minus e to the power minus tau nu. Now let us consider a material with no incident radiation coming from the left-hand side and ask, what is the specific intensity of this material? The material is at a temperature T and it is in thermodynamic equilibrium. This is the second term because the first term just drops out. There is no incident radiation. Now let us write this in the two limiting cases. In the case of an optically thick body, when the optical depth is very large compared to 1, the second term on the right hand side can be dropped. It tends to 0. Therefore, the specific intensity is just what you would expect from a black body at that frequency nu. But when the optical depth tau nu is much less than 1, I can expand the exponential and keep only the first term because the higher order terms in optical depth, tau squared, tau cube and so on will be even smaller and therefore can be neglected. And therefore what I will get is that 1 and 1 will cancel out and therefore I'll get the specific intensity is a fraction of the black body specific intensity, and the fraction is given by tau nu multiplied by the black body specific intensity, where tau nu is the optical depth. So these are the two limiting cases of an optically thick body and an optically thin body. Now the important thing to appreciate is that when the body is optically thin, which is the lower case, the radiation intensity, specific intensity, is always less than the specific intensity of a black body. It's only a fraction tau nu into I nu b. As the optical depth increases, this fraction will increase. And finally, when the optical depth tends to be very, very large, the specific intensity will tend towards the black body specific intensity. Let us state that more explicitly in the next slide. When the optical depth is very, very large, the body is tending to be opaque, the second term is 0, and we have the black body specific intensity. Now, therefore, the intensity from an optically thick body approaches the black body value as tau tends to infinity. Let me say that again. The specific intensity from an optically thick body will increase and tend to the black body value at that frequency as the optical depth tends to infinity. But it can never exceed this. The specific intensity can never exceed tau nu b, because the limiting case of tau being infinity, this term drops out and this is all I will get. So this is a very fundamental limit. It's known as the black body limit. The Chinese saying, one picture is worth 10,000 words, therefore let us look at this using a figure. What I'm saying is the specific intensity of an optically thick body will be tau nu into I nu b. What is plotted here is I nu b, the spectrum of a black body at a temperature T at all frequencies. What I'm saying is that our medium may emit radiation at various frequencies, this frequency or this or this or this. The specific intensity can have any value it likes depending on the mechanism and various other things, but it can never be greater than the corresponding value from a true black body, which is the value on the black line. In other words, it cannot be like this red bar over there. That is forbidden for a body in thermodynamic equilibrium. What will be the spectrum of radiation from an optically thin body when it is able to radiate at all frequencies? Well, it will be something like shown by this dotted curve. The actual value at any given frequency will depend upon what mechanism of radiation that we are talking about. But I would like you to notice that, well, two features. One is at all frequencies it can be less, it has to be less than the corresponding black body value at that frequency. But you notice that at extremely low frequencies it can equal the black body value. Why is that? Well, there is a medium with absorbers or scatterers with a mean distance between them. When the radiation has a wavelength small compared to the spacing between the scattering particle, the medium will be transparent or optically thin. But when the wavelength becomes very large compared to the mean spacing between the scatterers or absorbers, the medium will appear opaque. Therefore, at low enough frequencies, all media will appear optically thick. In other words, even though the medium is optically thin at higher frequencies, at these frequencies the medium will be optically thick in the sense that the specific intensity from the body will be close to the black body value. So stated once again, the specific intensity from an optically thick body approaches the black body value as the optical depth goes to infinity. It can never exceed this. So I say, what about a laser or a maser? You know that a laser or maser, before it starts lasing, will emit radiation like the neon light in your shopping district. Suppose we are considering a helium neon laser, you will find glow of red light just like in the shopping districts. But when it starts lasing, the intensity of that radiation will increase millions and millions and millions of times. It will far exceed the radiation from a black body at the temperature of the laser. The temperature of the laser will be room temperature, 300 Kelvin. In other words, a laser or a maser seems to violate this fundamental theorem that I have stated. It is able to violate it because a laser or a maser is not an absorber but an amplifier. The absorption coefficient is not positive, the absorption coefficient is negative. In case you have forgotten, let me remind you once again that we define the absorption coefficient alpha nu through this equation. The absorption coefficient is related to the loss of brightness in a beam, the loss of brightness d nu with a minus sign over a length ds. If certain fraction alpha nu, I nu is lost. And because I have the minus sign here and it is absorption, I have taken the absorption coefficient convention to be positive. But in a laser or a maser, which doesn't absorb but amplifies every subsequent slab, adds to the radiation and not takes away radiation, the absorption coefficient is negative. Or in other words, that equation can be written as di nu is equal to plus modulus of alpha nu I nu ds. Why is a laser or a maser able to violate this black body limit? That is because a laser or a maser, the atoms and molecules are not in thermodynamic equilibrium. The radiation from a laser or a maser is coherent radiation and not incoherent radiation as from the black body or the radiation from the sun. One astronomers talk of brightness temperature of a source. The brightness temperature, let us say, an astronomical body, you don't know what it is, you don't know what is causing the radiation, is emitting this much intensity at that frequency. The first thing an astronomer, particularly radio astronomer, will do is ask, what will be the temperature of a hypothetical black body that would emit that amount of radiation at that particular frequency? That is not the real physical temperature of the body. What is the temperature of a hypothetical black body that would emit that intensity at that frequency? And that is called as the brightness temperature. Now, if you calculate the brightness temperature of a laser or a maser, you will get some ridiculously large number like 10 to the power 20 Kelvin or 10 to the power 25 Kelvin. Clearly, the laser or a maser, your laser pointer, is not at a temperature of 10 to the power 25 Kelvin. It's at 300 Kelvin. So, when an astronomer finds that a source has a very ridiculously large brightness temperature, then the astronomer will conclude that the radiation is not incoherent radiation. Whatever may be the body, whatever may be the mechanism, the radiation is coherent radiation, like from a laser or a maser. We shall come back to this when we discuss radiation from pulsars. Now I have introduced the notion of absorption coefficient and emission coefficient. Where do they come from? Well, in classical physics, we use concepts like specific heat, electric and magnetic susceptibilities, dielectric constant, refractive index, etc. Classical physics does not tell you anything about the origin of these properties, nor does it tell you why it varies, why the refractive index of one glass is different from the refractive index of another type of glass, or how to calculate the dielectric constant or the refractive index or the magnetic susceptibility. So it is with absorption and emission coefficients. To understand these quantities and to calculate them, you have to use quantum mechanics. Right now, we are not ready to digress into that. If possible, little later on, I shall try to fit in one extra lecture in which we will discuss two very important concepts, the concept of spontaneous emission and stimulated emission. This was an important concept introduced by Einstein in one of his most important papers published just 1 year after the general theory of relativity in the year 1917. Now, the basic reason why absorption coefficient or emission coefficient or the optical depth will be functions of frequency. For example, it may be zero at most frequencies except of some discrete frequencies. Why is that? Quantum mechanics tells you that is because in quantum physics, energy levels are discrete of atoms, molecules, or any system, solids, energy, nuclei energy levels are discrete. Therefore, absorption and emission lines occur at discrete frequencies, but they do not occur at infinitely well-defined frequency or wavelength. The absorption line or the emission line has a certain width. And there are various reasons for this width. For example, Heisenberg's uncertainty principle itself tells you that these energy levels must have a width emanating from the uncertainty principle. Similarly, atoms and molecules are moving. That means the radiation that they emit will be Doppler shifted either to a higher frequency or to a lower frequency. Therefore, there are many reasons why the absorption lines and emission lines are not at like a delta function at one particular frequency. There is a spread in frequency. Now, where does the continuous radiation that comes from? Well, that may be due to entirely different processes. We will discuss that in a separate lecture on radiation from accelerated charges. Just to convince you, I have shown you 4 absorption lines, inverted, from rubidium atom. These are very high resolution spectra, and you see these absorption lines are not delta functions, they have a certain width. Now I could have also shown you emission spectrum of this element or some other element, they will also have a finite width. So please understand that the reason why absorption and emission occur only at discrete frequencies is from quantum mechanics, and quantum mechanics also tells you why there is a width to these absorption and emission lines. Now let's go back to the puzzle which we left unresolved in the last lecture. Why is it that when we look at the limb of the sun, the spectrum of light from the chromosphere, just before the totality of the eclipse, you see emission line? Let's try to understand this. Here is our good old equation of radiative transfer. The first term on the right hand side is the incident intensity attenuated by the medium. The second term on the right hand side is the intensity added by the medium but self-absorbed by the medium. Now when you are looking at the limb of the sun, there is no radiation coming from the background. In other words, there is no radiation coming from behind the sun. You are only detecting the radiation from the limb of the sun, the outer layers of the sun in the limb of the sun. Therefore, this first term, which represents the background specific intensity, is simply not there. Secondly, the solar atmosphere is optically thin. Its density is even less than the density of our atmosphere. And because the solar atmosphere is thin towards the limb, you can expand this exponential as 1 minus tau nu plus etc. and keep only the first two terms. And that's once again telling you that the background radiation is not there when I'm looking at the left limb of the sun, and that is expanded and keeping only tau. Tau squared is even smaller, tau is small, tau squared, tau cube and so on are ridiculously small and therefore we can be dropped. 1 and minus 1 cancels out. So I have only tau nu times I nu b. Therefore, what I would expect from the limb of the sun is a fraction tau nu of the Blackbody spectrum at the frequency nu if the limb were to be a true opaque blackbody at that temperature. Of course, it is not. Now, let us say, so what we get is tau nu into I nu b. Now, this is not a delta function at a particular frequency. This is a certain width. And that width is because of various reasons. For various reasons, the energy levels themselves have acquired a certain width. Now, if the optical depth in the limb of the sun is a little larger, then the amount of radiation I'll get will be larger. And therefore, the emission line will be more intense. Now, as I go on increasing the optical depth in the limb of the sun, the outer layers of the sun, eventually the limb of the sun will tend to become a black body. Therefore, the intensity of radiation that I will get will correspond to the black body. But please remember, the limb of the sun is not opaque. I'm just illustrating that the limiting value of these emission lines will be the black body specific intensity. So that's the reason why when we look at towards the limb of the sun, there is no background radiation, the medium is optically thin, and I get only tau nu times I nu b, I get emission lines. I hope that is clear to you. Now let us look at absorption lines when we look at the spectrum of radiation from, say, the central region of the disk of the sun. When we look at, say, the point A, there is background radiation. What is the background radiation? Radiation from the interior of the sun flowing through the outer atmosphere. That was not there when we looked here. There is nothing coming from there. But when we look there, the radiation from the interior is coming and going through the outer atmosphere. Therefore, the outer atmosphere attenuates the incident radiation and also contributes to the outgoing radiation. So there is incident radiation coming from the interior of the sun. This is the outer atmosphere of the disk, and this is the outgoing radiation. The equation of radiative transfer is the same as before, and because the upper atmosphere is optically thin, the upper atmosphere of the sun is optically thin everywhere, not just when you look at the limb, even when you look at the disk of the sun, the outer layers or tenuous optical depth is much less than 1. Therefore, I can expand this exponential and this exponential. This will become 1 minus tau nu. This will become 1 minus tau nu, and the 1 cancels out and I'll get only plus tau nu. And here I'll get minus tau nu. So this equation reduces to the specific intensity we will get will be the specific incident intensity from the interior of the sun multiplied by tau nu into, in square bracket, I nu 0, which is the incident intensity from the interior, minus the intensity contributed by the outer layers of the disk, atmosphere and the disk of the sun. Now, let us say we are at some frequency. At that frequency, the radiation coming from the interior of the sun has a value I nu 0. That is the first term in these equations. Now what we are interested is in the right hand side, which is the sum of the first term and the second term. And there is a minus sign. Therefore, there will be a tau nu into I nu 0 minus I nu b. So the depth of the absorption, the amount of radiation that is taken away from the background radiation, which is the radiation from the interior, is related to the optical depth. Just as the emission line intensity was proportional to the optical depth. When we increase the optical depth, the emission line intensity increases because tau nu into I nu b. This time, as the optical depth increases, the depth of the absorption line will increase. In other words, more radiation will be taken away. But please remember, in order for there to be a net absorption from what is coming from the interior, this term has to be negative on the right hand side. And there is a minus sign. But whether it stays negative or not depends on whether the square bracket is positive or negative. If the square bracket is positive, then there is a net absorption. If the square bracket is positive, what does it mean? It means that the specific intensity of the background radiation is greater than the specific intensity contributed by the atmosphere. Or in other words, the brightness temperature of the background radiation is larger than the brightness temperature of the foreground radiation. Then and then only you will get absorption. Imagine there is a truck with powerful headlights and you are a cyclist standing in front of the headlight with your cycle lights on. I will see you and the cycle light only in absorption as a silhouette. What I will see is a bright headlight of the truck. Why? That is because the brightness of your cycle light is less than the brightness of that truck's headlight. It is the same reason why you see firefly in your garden at night, but you don't see the firefly glowing during the daytime. So it's a question of whether the background brightness is larger than the foreground brightness or not. So once again, let me repeat, I will get a net absorption only if the background brightness is greater than the foreground brightness. In the case of the disk of the sun, that is guaranteed. As I said when we discussed limb darkening, we know energy is flowing out of the sun. Therefore, the interior is hotter than the outer regions of the sun. Therefore, I am guaranteed that the brightness temperature I nu 0 is larger than the brightness temperature corresponding to the radiation emanating from the outer atmosphere. So that is how one must understand why when we look at the disk of the sun, you see absorption lines, whereas when you look at the limb of the sun where there is no background radiation, you see emission lines. So let us end this discussion by once again looking at the equation of radiative transfer. There are two terms. I mu 0 is the incident intensity on the medium. That is attenuated by a factor e to the power minus tau nu by the medium. The medium is at a certain temperature T. If the medium were optically thin and opaque, it will contribute the black body intensity I nu b at that frequency, but it is not opaque. It has a certain optical depth. Therefore, there is a factor 1 minus e to the power minus tau nu. E to the power minus tau nu is the self-absorption by the medium. The medium adds, but also takes away a fraction of the radiation. So that is the equation of radiative transfer. I hope you will remember it forever and ever and understand that you can write it down from first principles. In the next lecture, we shall change gears. In the previous lecture, we discussed what are the stars. In the next lecture, we will discuss the following interesting question. Why are the stars as they are? In other words, why do the stars have certain remarkable properties they have? And to understand that, we have to discuss Eddington's theory of stars. Thank you very much.